Right now, BGP is so flexible that you can do crazy things, and there's no guarantee that these protocols will actually find a best route. They can just oscillate forever.
So things get stuck in a bit of a loop, do they?
They can. What's even more problematic today, because remember, okay, so maybe I didn't make this clear, but BGP evolved organically. Nobody had a model of non-distributive algebraic structures when they designed this protocol. It just evolved organically from a previous protocol. And so it wasn't based on some mathematical theory and, oh, we're going to implement that. That's true with some of the other protocols, like the shortest path protocols that are used inside of networks. They came from Dijkstra's algorithm, things like that. We had a model, and then people implemented distributed algorithms to implement that model. But in BGP, we just had the protocol evolve, and with no model.
So perhaps two guys at different companies said, hey, we need to get our service talking. I'll do this, you do that.
Yeah, and they would go to the Ciscos of the world and say, can you add this hack? Can you add this feature? And so we've had this kind of a lot of expedient extensions to the protocol to solve various problems. And now when you look at the policies that people are using in the BGP world, they're quite complicated.
Is it amazing that it works?
It is kind of amazing, yeah, but it also requires quite a few operators, systems, people that keep it working.
So people are there tweaking things.
Yeah, there's a lot of manual intervention and constant monitoring, and that happens. It would all collapse without human network operators keeping it working.
Because I'm making the parallel, perhaps it's a bit obvious, but of the road network and all these motorways or freeways, call them what you will, and various other roads, and when something goes wrong with one road, everyone has to get diverted and all this kind of stuff. Is it a similar thing on the internet?
It's a similar thing, except, for example, normally when you're driving, you can essentially take any road you want, okay? But to use the analogy for the internet, if we're driving, it would be like, well, you came from here, so you can't use this road over here, right? That road is prohibited from you because you came along this path. You can only use these paths because...
So you're from that town, you're not allowed to use that road.
That's right. That's the kind of thing that happens in the internet routing. So the big problem that I've been working on for a long time now is there's all this algorithmic and work done on semi-ring, finding shortest paths with semi-ring, like algebraic structures. But I'm going to try to model structures that don't have this critical property of distributivity. Can I still do something with Dijkstra's algorithm, with Bellman-Ford, even though all of the mathematics of the semi-ring world is all based on this distributivity, which I'm throwing out the window? It turns out that you can actually make some progress, that you can actually get something done. And we've shown that, with certain non-distributive algebras, if you will, we can still find solutions that make sense. They don't have the same interpretation as best paths did before. For example, in the semi-ring world, when you solve these problems with, let's say, Dijkstra's algorithm, you get the best paths over all possible paths. But when we throw away this distributivity, what we get are the best paths that you can get given what your neighbors have given you. So it's kind of like a local, I'll call them local optima. They're the best thing you can do given what your neighbors have given you. It's kind of a think of it as kind of an equilibrium point, right? Your neighbors if their neighbors don't change, this is the best you can do. It might not be the best possible path, right? It might not be the best possible path over all possible paths, but it's the best you can do given what your neighbors have given you, okay? So it's a different kind of notion of best path. And it's actually the one that's appropriate to interdomain routing. So like in the interdomain world, it doesn't make sense to talk about globally optimal paths in a world where there's no agreement right? Nobody's going to agree on what the metric is, a global metric. I must admit that I'm trying to take this problem I'm trying to be inspired by BGP and then take it back to sort of I want to take it back to the world of graphs and paths without kind of thinking about all the domain-specific detail of the BGP world. And can we take, suppose we come up with new math and new stuff in this world of non-distributive algebraic structures, can we take that back to BGP? Maybe. It's going to be very hard, though, because BGP is already such a legacy protocol. It's very hard to make changes in that world.
So you're thinking about what might be next, right?
I'm thinking about what might be next. I'm thinking about maybe we can apply this to other problems like circuit layout, like social choice problems, aggregating social choice. Or maybe we can apply it to other combinatorial problems that have nothing to do with interdomain routing. That's what I'd like to do, actually. Because I think the interdomain world is a bit, you really can't make any changes there anymore. I mean, there are problems like security that, people have come up with solutions for, but that haven't been deployed just because it's so difficult to get all the players working together in the global internet.
So one of the big challenges, by the sounds of it, is everybody's got their own agendas, right?
In the global internet, yes.
Yeah, so everyone's got their own agenda. So whatever the commonly used protocol has to kind of take some of that into account, but also not take it into account. Would that be fair?
There's a balance. You want to allow each network to tailor its, let's call them routing policies, or routing policies. Sorry, I've been in the UK for 12 years, so I'm saying routing now. But routing policies, we want them to be flexible because in the interdomain world, you're going to have disagreements about what best routes are. Right now, I'm working on proofs that what happens is that we're using these same algorithms, like Dijkstra's algorithm, Bellman-Ford, and proving that they work with these non-distributive structures in some cases, but they give you these local optimal routes, not globally optimal routes. So we're working on some of the mathematics there because we'd like better complexity bounds on these algorithms. Also, we're looking for other applications. So I've been looking at things like circuit layout and other kinds of applications that are far removed from internet routing. I'm hoping we can extend some of the work on semi-rings and that kind of thing to extend it to these slightly more exotic structures that don't behave as semi-rings do, right? So, and then people, maybe they'll never know that it was inspired by this bizarre protocol called BGP. And I'll try to explain informally why not.
What doesn't fit? The
As you can
BGP
see, this involves interaction between different entities. What a sensor can do is that it can block the user's connection at this point.